Hello, I'm Tate from the University of California, San Diego, and I'll be presenting to you work I did with Chen and Hawblitzel for Microsoft Research on inferring object-oriented typed assembly languages. So compilers are these great things which take nice, easy-to-write C# code and turn it into hard-to-write assembly code for us. However, occasionally they make mistakes, and those mistakes can introduce vulnerabilities at the binary level that hackers can exploit. One way to address this is to use a typed assembly language, which includes a proof that the binary code is safe. This proof is verified by a trusted proof checker, so that there's no need to trust the compiler itself. Certifying compilers are those which generate such typed assembly language. They traditionally use a technique called type preservation. A type preserving compiler outputs x86 as well as types or proofs that x86 is safe, which are then handed off to a proof checker for verification. To produce that x86 with types and proofs, inside there are many layers of intermediate representations along with the types and proofs that those representations are safe. And together these have to be optimized and converted through the various stages. And it can be quite a burden to do this for all these stages, which makes it hard to adopt these types and proofs into existing compilers. Furthermore, the final types and proofs output increase the size of the executable file. To address these problems, we recognize that those types and proofs can be broken up into two classes. Signature information, which is rather high-level stuff like classes and function signatures, and low-level stuff like types and proof annotations on the specific assembly instructions. Furthermore, in a traditional compiler that only outputs x86, inside the signature information is already present through all the various stages. So it's pretty easy to extend such a compiler to output that signature information to a file. Our idea then is to simply add type inference to infer the missing proof annotations, which can then be handed off to a proof checker for verification. This requires little change to existing compilers and also makes the x86 have a much smaller annotation size. The big question then is, can inference be effective enough to pull this off? To assuage your fears, we ran our type inference algorithm on a number of benchmarks taken from prior research in this area. We found that we were able to infer the missing type annotations for 98% of the methods. In fact, we are capable of type checking all of the C# features except for exceptions and delegates, and those are matters of implementation. They're not due to any theoretical limitations. So yes, type inference is effective enough. So now, let's take a look at how we type C# at the assembly level. Let's start off with some bad PseudoAssembly code for C#. Here's a function which takes two lists A and B. It starts off by grabbing A's vtable, and from that, it grabs A's implementation of the isEmpty method, and then calls A's isEmpty method with B as the this pointer. This seems fine since they're both A and B are both lists, but in fact this is unsound. The reason being that A could be an array list, and B could actually be a linked list. And so A's implementation of isEmpty may fail to work on B. In prior work, what we did to identify that this program is broken is first, we made the function signature more specific. Then we inserted a bunch of pseudo instructions to help the type checker verify the program. This existential type indicates that A and B are each instances of some, but possibly different, subclass of list. Before we can use A, we have to open its existential type, so that A is an instance of alpha, where alpha is some fresh variable, but which is known to be a subclass of list. Then, using signature and memory layout information, we can figure out that VT is actually the vtable for alpha, and MP is a method pointer whose this pointer is expected to belong to specifically alpha, not just to list. Next, before we can use B, we also have to open its existential type, so that B is an instance of beta, where beta is some fresh variable known to be a subclass of list. This pack instruction then checks to see whether B is an instance of some class beta, or gamma, which is known to be a subclass of alpha. This check fails since B is an instance of beta, but beta does not extend alpha, it only extends list. And so our traditional typed assembly language would reject this program, as we would like. Of course, to pull this off, we had to insert a number of pseudo instructions which had to be preserved all the way from the C# level. So instead, in our Inferable typed assembly language, we're able to remove all pack annotations, all open annotations, and furthermore, we didn't even need loop invariants, which I didn't show you here. Instead, we chose to use type inference. So our inference strategy was to always open existential types as soon as possible. And then instead of using pack and open operations, we used this subtyping rule here, which says that given a valid subtyping or substitution of the bound variables in the two types, such that the two bodies of the types are subtypes of each other after substitution, then the two existential types are subtypes of each other. This one rule subsumes both open and pack. We then use abstract interpretation over existential types, which requires subtyping and join algorithms. This is problematic because subtyping alone is undecidable for bounded existential types. So we designed a category theoretic framework for existential types, which is both constructive and that includes abstract algorithms for inference, as well as instructive in that it gave us a number of guidelines to help us design our type system. So here's how we type check that same example using our inferable type assembly language, which we called iTalX. First, we follow our inference strategy and immediately open those two existentially typed variables, A and B, so that A is an instance of alpha, which is fresh in the subclass of list, and B is an instance of beta, which is a fresh in the subclass of list. We then use signature information to figure out that VT is the vtable for alpha. And similarly, we use signature information, the fact that alpha is a subclass of specifically list, to figure out that is empty is a method pointer whose this pointer is expected to belong to alpha. Next, for this function call, we type check that instance of beta is a subtype of this existential type here, indicating that it must be an instance of some subclass of alpha. This check fails since beta does not extend alpha, it only extends list. And so iTalX would also reject this program without the need of type annotations. Now for evaluating iTalX, first we looked into the expressiveness. iTalX is capable of handling many features. As I said, basically all the features of C#, some of which are new for type assembly language, such as generics and complex stack manipulation. So that means that not only do we make it inferable, we actually extended the expressiveness of our type assembly language. iTalX is also designed to be robust with respect to many optimizations, such as loop induction and variable strength reduction. And iTalX should be able to handle the remaining features, as I mentioned earlier, such as delegates and exceptions. And as I said earlier, experiments showed that iTalX is able to verify 98% of methods, and the last 2% will be covered once we get the delegates and exceptions working. So for iTalX efficiency, we compared its inference time with the compilation time of the program as a whole, and we found that on average, inference time only adds 8% to the overall compilation. And so inferring assembly level types is an affordable process that could be incorporated into the compilation pipeline. As for type annotation size, we compared iTalX with our traditional type assembly language that was developed before, and we found that on average, our assembly size is only 2/5 of what it was before. And so we significantly reduced type annotation size by making our assembly language inferable. As for the burden of implementing our new type assembly language, we compared with the old type preservation method. To change an existing compiler, namely Bartok, it used to take 19,000 lines of code that had to be changed. Whereas for our thing, we only need 5,000 lines of code. Furthermore, those 19,000 lines of code cut across the entire code base, whereas our 5,000 lines were just a module addition to code base, namely to output the type signature to file. Our type checker before was 13,800 lines of code, but now including inference, it's 15,100 lines of code, and these two portions could be separated to reduce the trusted computing base size. So in conclusion, type inferences at the assembly level is expressive enough to verify C#, including optimizations. It's flexible enough to accommodate new language features as they come. It's efficient enough to use regularly during compilation, and compact enough to include in executable binaries as we ship them out. Lastly, it's modular enough to retrofit existing compilers with, which is probably the most important aspect of this research. Thank you for listening, and feel free to contact me about any questions.